continue with the third research paper. The paper is by Yuezihan Yang, Changyu Li, Gaode Chen, Peiyi Li, Zhang, Jingjian Lin, Peng Yang, Sun, Wentao Zhang. The name of the paper is MMGCL, Meta-Knowledge Enhanced Multi-View Graph Contrastive Learning for Recommendations. Let's leave the stage to Gaode Chen. No?
Yuezihan Jiang. Thank you. Okay. Good afternoon, everyone. I'm Yuezihan Jiang. Today, I'm excited to present our work titled MMGCL, Meta-Knowledge Enhanced Multi-View Graph Contrastive Learning for Recommendations. In this presentation, I'll first discuss the motivation behind our work, then briefly cover some preliminaries. I'll then dive into our proposed method, share our experimental results, and conclude with our main contributions. Let's start with the motivation for our research. Multi-view graph learning has shown remarkable success in recommended systems, particularly in click-through rate prediction tasks. It allows us to capture complex relationships between users and items across different perspectives of views. However, when applying multi-view graph learning in real-world industrial recommendation scenarios, we face two significant challenges. First, there is the issue of multifocal, multi-source data noise. The noise stems from various sources and can manifest both within individual views and across different views. Second, we encounter multi-source data sparsity, which is particularly problematic in multi-view learning scenarios as it requires more model parameters to learn from multiple views. We experimentally illustrate these problems. In the left figure, we present the performance of a state-of-the-art multi-view graph learning method under various edge noise configurations. The x-axis shows the proportion of noisy edges of the user item graph comparing to all noisy edges. Y-axis shows precision at 10 performance. We observe that noise combined from multiple views are more harmful for model performance. It experienced the most substantial decline in performance when the edge noise comprised 15% of both the user item graph and the item graph. The decline occurs because multifocal noise introduces inconsistencies across different views, thereby amplifying data noise and adversely affecting performance. The right two figures illustrate the data sparsity problem. We did an experiment when we randomly removed some labeled samples or edges in the Flixer dataset to create different levels of sparsity. The x-axis represents the removing proportion, and the y-axis represents the performance. We then added a consistency check to produce a variant model, making sure that predictions match across different views. The results show that the variant model with consistency constraints did better than the original model, even with fewer data points. This shows that adding extra supervised signals and self-supervised meta-knowledge help dealing with data sparsity and improve the model performance. To address these challenges, we propose two key strategies. To mitigate the multifocal, multi-source data noise, we utilize a meta-view representation. This provides high-quality self-supervised signals for denoising each individual view. To tackle the multi-source data sparsity problem, we introduce a meta-knowledge transfer contrastive learning approach. This is not only fully utilize self-supervised signals, but also reduce the search space for model parameters, effectively addressing the data sparsity problem. Before diving into our method, let's quickly cover some preliminaries. In our problem formulation, we are dealing with multiple graphs representing different views of user item interactions. Our goal is to leverage these multiple views to improve recommendation accuracy. Now let's explore our proposed method in detail. Here is an overview of our MMGCL pipeline. We start with a graph encoder to generate node representations. We then extract meta-knowledge to construct a meta-view from our individual views. Using this meta-view, we perform graph denoising to discard noisy or conflicting edges. We then apply knowledge transfer through contrastive learning to integrate meta-knowledge. We also preserve view private knowledge to maintain the unique aspects of each view. Finally, we apply task supervision for the recommender tasks. In the meta-knowledge extraction phase, we generate customized transfer networks for each view and combine them to construct our meta-view representation. Specifically, we create customized transfer networks for each view by view-specific MLPs and aggregate the customized transfer networks to form the meta-view by aggregate component. For meta-knowledge-aware graph denoising, we use the meta-view representations to remove noisy edges within views and conflicting edges between views. We calculate edge weight and reweight them based on the meta-view information. Edges below a certain threshold are removed. In the meta-knowledge transfer contrastive learning step, we address data sparsity by leveraging high-quality self-supervised signals. We perform contrastive learning optimization between the rectify views and the meta-view. We take a view private knowledge preservation loss to avoid the trivial solution that the representations of every view becoming too similar to one another. For recommendation optimization, we incorporate supervision signals on both rectify views and the rectify meta views using the info NCE loss function. Now let's look at the experimental results. We evaluate our method on both open benchmark datasets like Flixster and MovieLens and industry datasets like Huairent. We compare MMGCL against various baseline methods, including general GCL methods, multi-view GCL methods, and graph denoising methods. We use standard evaluation metrics such as hit rate and DCG, precision, and recall. Our end-to-end comparison results show that MMGCL consistently achieved the best performance across all datasets. Notably, multi-view GCL methods generally outperform GCL methods, indicating that incorporating multiple graphs brings information gain. Besides, our graph denoising results demonstrate MMGCL's superiority in robustness to noise. With 16% noisy edges, MMGCL's precision at 10 only dropped by 1%, while other methods dropped by more than 3%. These results highlight the crucial role of our denoising components and show that MMGCL outperforms both general and multi-view denoising approaches. Regarding data sparsity, our results show that MMGCL's meta-knowledge transfer approach outperforms other multi-view GCL methods using interview contrastive learning. We testify the effectiveness of meta-knowledge transfer contrastive learning by adding the optimization process to other baseline methods, and the result is in the figure. It can be found that the meta-knowledge transfer enhanced performance across all tested methods, demonstrating its effectiveness in capturing comprehensive relationship among views. Finally, let me summarize our main contributions. First, we identify the challenges of multifocal multi-source data noise and multi-source data sparsity in multi-view graph learning for recommender systems. Second, we propose novel methodologies, meta-knowledge-aware graph denoising, and meta-knowledge transfer contrastive learning. Third, we have successfully implemented MMGCL in a leading Chinese short video platform, demonstrating its practical value. Lastly, MMGCL achieves state-of-the-art performance, outperforming baselines on both benchmark datasets and real-world A/B tests. And thank you for listening.
Thank you. Thank you. Okay, we have time for a couple of questions. Do we have any questions from the audience here? Any questions? Please raise your hand. In the meanwhile, I have a question from the remote audience. The first one is, can you give more details about the info NCE loss that you have used, and how has it been implemented, and why do you need it?
Sorry, could I just see the question?
The info NCE loss, more details about that, the implementation, and why you needed it.
The question is why we use info and CE loss. This is because we use info and CE loss as a base loss function, base optimization in our method, and it is a popular recommended optimization way in real industrial setting because we may choose the negative samples within a batch, within a data batch to serve as the negative samples, and it may eliminate the popularity bias, and maybe it is more friendly to new items, which may be economical and more friendly to real industry settings because it has many new items every day. I don't know whether...
I think so. Any questions? Okay, I have just a curiosity. In your paper, you mentioned that your model has been deployed in a real industrial recommender system in China. Can you give us more details about this deployment, challenges, data scaling?
Okay. Maybe this is about the cost of deploying Jiang system in real industry settings, right? Actually, we catch the because in the online training platform, the data comes in a streaming way, and we just take a snapshot for a period of time to collect the data for graphs. And every time we train, we use the period of times graph to train, and the snapshot will be updated for a certain time. So during a period of time, it won't be updated, and we can use the cache data, so it won't bring much cost because the data won't be updated during the training time.
Okay, thank you. We are perfectly on time, so thank you again.